Okay, sir. Good afternoon, everyone. Myself, Dr. Sachin Kumar, Assistant Professor in the Blush University. Today, I'm here to present a lecture on carbon nanomaterials, pioneering sustainable solution for a greener future. It's a NDL Club event. Hopefully you like it. So, first of all, when we talk about sustainability, we talk about sustainability development goals. There are 17 total sustainability development goals, uh, as you see in your screen. First is no poverty, then zero hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable and clean energy, decent work and economical growth, industrial infrastructure, reduce inequality, and so on. But we need this sustainability goal because of the problem we are facing today. That is deforestation, waste disposal, air pollution, global warming from fossil fuels, climate change, biodiversity loss, water insecurity, and plastic pollution. Plus, poor health, short life expectancy, little or no access to relevant education and skill training, and gender and cultural equality. So these 17 goals interconnected and success in one can bring the success in other. Science and technology are considerably striving to contribute to advances in good health. That is point three. Then clean water, point six. Energy and environment, innovation infrastructure and responsibility consumption and production. That is 17, 13, 14, 15, 9, 11, and 12 point of sustainability development goals. Success here will lead to the reduced poverty and hunger, improve equality, education, and economical growth, which in turn will lead to the ultimate universal goal, peace. That ultimate universal goal, that is peace, justice, and strong institute. The best way to approach these goals to assemble well-balanced teams, that's point 17, to tackle current need with emerging and existing global talent. Now, when we talk about science and technology, nanotechnology is one of the most promising key enabled technology of the 21st century. The field of nanotechnology was foretold in Little Famous 1959, where he said there are plenty of room at the bottom. Uh, Nanotechnology fields are now approaching more than 50 years of research and application, continuously expanding, contributing to almost every field of science. That is natural science and engineering, material science, medicine, agriculture, information and communication technology, and list is still going on. Nanotechnologies started coming into the own in 1980, gaining public exposure and awareness, include having to navigate some controversy and commercial application of the new technology began. Now, the society is facing serious, grave challenges. We have to look at new technologies to offer solution to almost every aspect of health, energy, climate, and environment, either directly or indirectly. Then, why is nanotechnology? As we previously discussed, instead of incremental improvement to existing technologies, nanotechnology offer disruptive, game-changing breakthrough and innovation that can provide immediate answer and solutions to the health of our society, environment, and the planet. Area in which nanotechnology advance are making difference, including energy, environmental protection, source management, and healthcare through the development of smart material and connecting devices. Furthermore, nanotechnology as a field have developed communication skills to bring scientific, engineer, medical, and other communities together and have thus impacted many related fields. Now, when we talk about nanotechnology, we talk about nanomaterials. What are the nanomaterials? Nanomaterials have emerged as an amazing class of material with at least one dimension range of 1 to 100 nanometers. As you see in figure, there are molecules as 10 to the power minus 1 nanometer, then DNA is 10 nanometer, virus is 100 nanometer, and after that, bacteria is 1 micrometer. These are sizes of these different molecules or species. What make nano material different is exceptional high surface area. Every nanomaterial has exceptional high surface area, which is achieved through the rational designing of the nanomaterials. Furthermore, nanomaterial can be produced with outstanding magnetic, electric, optical, mechanical, categorical properties that are subsequently differ from their bulk counterparts. The nanomaterial properties can be tuned and desired by precise controlling the size, shape, synthetic conditions, and appropriate functionalizations. Now, classification of nanomaterials on the basis of nanomaterial can be classified on different types. When we classify on the basis of structural configuration, there are different types of nanomaterials like carbon-based nanomaterials. Example is fullerene, graphene, carbon black, um, carbon nanotubes, carbon fibers. Then in case of organic, they are ferrite, micelles, lipomers, living nanomaterials. Then in organic nanomaterials, metal-based, metal oxide, metal sulfide, ceramic, semiconductor, these are inorganic nanomaterials. Then composite, which are the mixture of 2 or 3 nanomaterials. Then on the basis of dimensions, when we talk about dimension, there is 0 dimension nanomaterials, which is like a point. Then 1 dimension nanomaterial is like a line. So nanorods are 1 dimension nanomaterials. Then 2 dimension nanomaterials, they are sheet-like structure, which has length and breadth. So graphene is a 2 dimension nanomaterial. Then 3 dimension nanomaterials are cubes, different type of big rods. These are 3 dimension nanomaterials. Carbon fiber is 3 dimension nanomaterial. Then based on core dimensions, we can classify them in microporous, isoporous, or macroporous, depending on their pore size. Then based on origin, artificial or natural, nanomaterials were produced by nature in naturally, as we see in magnetite, these are example of natural nanomaterials. Then alum powder, these are the natural nanomaterials. Other than natural materials is the artificial nanomaterials, which are produced by humans. Currently, we are producing artificial nanomaterials. Then based on potential toxicity, there are different type of nanomaterials, CMAR, biopersistent, granules, fiber-like. These are the classification based on potential toxicity. Now, what is carbon nanomaterial? There are different type of nanomaterials, but we are focusing here only carbon nanomaterials. Carbon nanomaterials have attracted increasing attention due to their unique structure, regularity, high effective active surface area, electric conductivity, chemical inertness, biocompatibility, mechanical thermal stability. Carbon nanomaterial are class of advanced material composed either of large carbon atom arranged in a nanoscale structure. Uh, Thanks to their unique properties, these materials can be used in diverse fields like electronics, energy, medicine, catalysis, and environmental protection. We discuss important. These are the different type of nanomaterials: nanodiamonds, fluorine, then carbon nanomaterials, single wall carbon nanotubes, multi-wall carbon nanotubes, graphene. These all are different type of nanomaterials. Then when we if we want to study the property of nanomaterial, we are taking a graphene as example. Key property of graphene is in case of mechanical strength, they are 100x stronger than the steel. Elastic modules, we see the elasticity of the nanomaterial is 1.1 TPa. Then tensile strength is 125 GPa. Hydrophobicity, thickness, addition force depend on their thickness. They are hydrophobic in nature, uh, but when they are agglomerated, then they are lose their this property. Then graphene is very thin with a large visual atomic thickness of 0.345 nanometer, very thin, single layer atomic layer of carbon-based nanomaterials. The thermal conductivity of graphene is 5,300 watt per MK. Then graphene is 97.7% transparent. So used in displays, as we previously discussed, the exceptional flexibility and robustness due to their sigma bonds, they are extremely flexible, extremely robust, not easily breakable. Graphene is a zero overlapping semi-metal, very high electrical efficiency. It's used as a superconductor material because of yes design. They are strongly absorb wavelength of all lights. So they are optically active materials. And if they are not optically active, some materials are not optically active. The use some chrome films to make them optical. So by designing them, we can also manipulate the properties. Then why carbon nanomaterial? There are different type of other nanomaterials, but carbon nanomaterial is extremely light yet strong. Other nanomaterial are often heavy. Then mechanical strength, very high tensile strength. Other nanomaterial weak in comparison. Electric conductivity is exceptional, as we previously discussed, whereas other nanomaterials are semiconductor or insulators. Thermal conductivity high, very high. Other nanometer often low. Surface area is very high. Therefore, it is using sensors or catalyst activities. Other nanomaterial is usually low. Flexible, mechanical flexible, other are brittle. Biocompatibility can be turned into biocompatible materials. Some are toxic and reactive. In some cases, carbon nanomaterials here also show some toxicity, but if we use it judiciously, it will not affect us. Then eco-friendliness can be made from biomass or waste carbon. We can use waste to produce carbon-based nanomaterial, where often other nanomaterials are rare. They are rare in nature. They are toxic metals. So that's why we use carbon nanomaterials. Then synthesis of carbon-based nanomaterials. There are several methods to synthesize carbon-based nanomaterials. We are discussing mainly graphene methods to synthesize graphene. So chemical vapor deposition, it's involved depositing gaseous reactant onto substrate. Then advantage of this method is producing high quality graphene CNT on the larger scale. Or limitation require precision control. Over the process conditions. Then other method is mechanical exploration, involve peeling layer of graphene from graphite, produce high quality of graphene not suitable for large scale production. Then reticule growth, involve growing graphene on a substrate using different template. Template is a mesh-like structure, if we can imagine. It's provide the considered desirable product. Product is highly quality graphene, required a specific type of substrate. Then pyrolysis involve the heating of organic compound to high temperature without the presence of oxygen. Advantage of this process is producing graphene from a wide range of precursors. Different precursors we can use to produce this type of graphene. Uh, Controlling the quality and property of the resulting graphene can be challenging in pyrolysis process. Then other is electrochemical process involve applying electric current to the graphite in a solution. It produce a graphene in large quantity, but the quality of graphene may be vary, depend on process. Other is rapid thermal annealing involving heating a substrate coated with carbon-containing layer to high temperature. Produce graphene quickly. Require precision over process conditions. Then biomass pyrolysis, similarly pyrolysis method, but here we use the biomass as a precursor. It is green and sustainable method, but the quality, the property of the resulting graphene is very vague. Quality is not so good. It needs further research. Then hydrothermal and solvothermal techniques involving reacting precursor in a solvent at high temperature and pressure produce a wide range of nanomaterials require specific equipment. Hydrothermal method, here we use the water as a solvent, the solvothermal we use other uh, solvents other than water. Microwave and ultrasonic irradiation involve using microwaves of ultrasonic energy to drive chemical reaction, produce nanomaterial quality, but required specialized equipment. Then further is arc discharge, involve getting an arc between the two carbon electrode in an inert gas environment, produce high quality of graphene not suitable for large scale production. It's only suitable for low scale production. Unzipping nanotubes, we can also use carbon nanotubes and unzip them and produce graphene. It produces high quality of graphene, requires special equipment and conditions. Then microwave synthesis, this method involves microwave energy to derive chemical reaction that produce graphene quickly, requires specialized equipment. The hammer method, most used method is hammer method. This method provides oxidizing graphite to produce graphene, which can then be reduced to graphene. It is simply and cost-effective method. The resulting graphene will not have the same property as pristine graphene. Then thermal decomposition, this method involves heating a carbon-containing compound until a decomposition decomposed to form graphene. Produce graphene from a wide range of precursors, controlling the quality and property of this resulting graphene can be challenged. Then electrolysis. This method involves applying an electric current to a solution containing carbon precursors. Produce graphene in large quantity, the quality of graphene can be varied. Then green synthesis, this method involves environmental friendly process to produce graphene, a suitable method, but the low quality, the property of resulting graphene is fair. Now, this is the carbon nanomaterials. Now, what is the application of carbon nanomaterials? So, first of all, health applications. Uh, Phonetics is a precise medical strategy that uses a single agent to perform, to diagnose, deliver treatment, and monitoring therapeutic response in the real time. So, as we see in this figure, um, nanomaterials are used to targeting different diseases, molecules, viruses, and they also use as a carrier to carry the drug to this target muscle or body part. Then they also used for cellular therapy. We deliver drugs to the particular disease containing cells or organs. Then cellular therapy is still going on. Meantime, they are also photodynamically or photothermally uh, detected. In vivo imaging are also provided by these carbon-based nanomaterials, imaging, optical imaging, and cellular imaging. So, in this health application, we simultaneously targeting the muscle, treating the drugs, and still monitoring the therapy which we are providing. Effects, how effective this therapy are or not is find out in real time. Then other tissue engineering at different parts, uh, dental tissue engineering, where we use carbon nanomaterials, then skin tissue engineering, neuron tissue engineering, and bone tissue engineering. In all these parts, we use nanomaterials or slightly carbon-based nanomaterials. Then energy applications, energy storage application or energy applications. In this category, uh, battery materials are, as we know, we still use carbon-based batteries, which are very inexpensive than when we compare with them lithium-ion batteries. So, uh, carbon-based nanomaterials are used in battery materials, and still research are going on to advance them. Then supercapacitor. Supercapacitors, these are the material which give known as a supercapacitor or electronic capacitor. They are energy storage devices that bridge the gap between conventional capacitor or battery. They are characterized by their ability to store and release energy rapidly, making them ideal for application required quick burst of power. So carbon nanotube, graphene, activated carbon, these are all are used for supercapacitor applications. Then fuel cell. Fuel cell uh, is uh, fuel cell is a cell where we use hydrogen and oxygen and create energy from them. So hydrogen-based fuel cells, they are methane-based fuel cells, and fuel cells are non-commercial energy. They are pollution-free energy. Uh, Carbon nanomaterials, mostly CNT or carbon nanocomposite, are anodic material in these fuel cells are used. Then solar cell, Probastic nanocrystal, TiO2 nanonodes, these are commercial solar cell materials. Now, carbon nanotubes, quantum dots, carbon nanotubes, graphene, fullerene, nanohybrids, they are all are used as a solar cell and perform better, uh, not worse. Photovoltaics, CM implies carbon nanomaterials used as an electrode, transport layer, active layer, or intermediary layer of solar cells. Then thermoelectronics. In thermoelectronics, we use different type of material, but the CNT and graphene show promising results. Thermoelectronics are technology where we convert waste into electricity, waste heat into electricity. Then further is hydrogen production or storage. Molybdenum disulfide, nanosheets, metal organic frameworks. These are used previously for hydrogen production and storage, but now carbon nanomaterials, mainly CNT and graphene nanocomposition, are used for this, for the catalyst and electrolyte water scaling, hydrogen storage, or hydrogen reduction reaction, oxygen reduction reactions, so on. Then carbon nanomaterials also used in piezoelectric or turboelectric materials. Previously, that are known nanometers, PVDF nanofibers are used for this kind of applications, but now uh, carbon materials show promising result for this. type of instrument. Then further is photocatalysis and electrocatalysis. Usually we study fuel cell, which is also electrocatalysis. Or maybe photocatalysis. But there are more application of photocatalysis and electrocatalysis by carbon nanotubes, such as carbon dioxide gas, vegetable oil gas, greenhouse gas. It's converted. It can be converted into the methanol and other valuable products such as carbon monoxide, formic acid, methanols, and methane. So we had carbon nanomaterial act as a catalyst to convert CO2 gas into valuable products. Similarly, other harmful gases can be converted into value-added products such as ammonia, methane. These gases also converted into valuable products by using carbon-based nanomaterials. Electrocatalysis and photocatalysis also used in wastewater treatment. Um, Wastewater, there's different type of wastewater, industrial wastewater, domestic wastewater, urban wastewater, municipal wastewater. So all these wastewater containing biomass and different materials, we can use electrocatalysis or photocatalysis to purify this water sources or also converting this organoid into valuable products. Graphene and the carbon materials are excellent option for these purposes. Now, main important application of carbon-based nanomaterials is that because of they are highly conductive, they are highly efficient, they are highly flexible. These materials can be used for the sensing, for the detection of harmful chemicals or pathogens or hazardous materials, pollution indicators. So um, when we want to sell something, we have to rely on the physical property of that material. So physical property, we can sense cyclometry, color of the material, or pressure, mass, strength, or acoustic waves. We are different type of sensor from them. Carbon nanomaterials are used for every type of sensor, physically, electrically, and optically. Electrically is more explored than physically and optically. Recently, optical sensors are more famous. Fluorescence, luminescence, phosphorescence, Raman, reflecting index. They are used different type of techniques, spectroscopy, interferometry, epiphotometry. These techniques are enhanced. These techniques will be enhanced or by using carbon nanotube with them. So sensing is the other use. We want to sense air pollutants, different soil pollutants, water pollutants, different hazard materials, different type of microbes. So sensing is an important part of carbon-based nanomaterials, or it's the application of carbon-based nanomaterials. Then carbon nanomaterials are also used in electronics uh, for wearable electronics. The electronics we wear on our body, and which give different measures of like sugar content, how much sugar content in your body, uh, different blood pressure, BP, different physical physiological activities measures. Then flexible batteries. These material can be used for making flexible batteries. So can it's easy to manage them or develop instrument with them. Then carbon-based nanomaterial, mainly graphene is used for touch screen, um, as we see in some figure where we see the glass transparent material which is folding. These materials carbon-based nanomaterials or mainly CNT or graphene. Then flexible transparent memories, we can form different type of flexible memories, different flexible RAMs, hard drives, and printable electronics. We also print circuits with these carbon-based nanomaterials. So it make the equipment or electronics small in size, flexible, easy to use, or carry on your body. So this type of things. Furthermore, in this figure, we see different type of materials we have based on, which are made by the carbon-based nanomaterials, like memory devices, image storage devices, displays, um, different uh, type of steam sensor, pressure sensor, temperature sensors, and so on. Furthermore, other applications, the filtration potential of carbon-based nanomaterial has been extensively studied, highlighting their effectiveness in purifying both air and water. So currently, there are so many filters which use carbon-based nanomaterial for their filtration process. And carbon fibers are widely used in the automobile industry due to their lightweight and high strength properties. Uh, Then furthermore, carbon nanomaterials have been explored in CH activation, bond activation, showing promising application in the chemical industry for efficient and sustainable synthesis. These are using organic reactions. Then carbon nanomaterials also play a crucial role in defense and aerospace sector where advanced materials are essential for performance and durability. These are the other applications of carbon-based nanomaterials. So what is future perspective? We have to synthesize new carbon-based nanomaterials or new technologies which are eco-friendly synthesis method. We have to develop them. Then we have to develop bio-driven carbon-based nanomaterial. There are so many carbon-based driven nanomaterials are currently in research community, but these processes are still far from complete research or complete product. Then hybrid composite for green technology. We have to produce some composite materials for greener technology for sustainable development. Furthermore, if I want to conclude my presentation, carbon-based nanomaterials represent a powerful class of material with vast potential of revolutionizing industry through sustainable high-performance solutions. These unique structure and functional properties make them ideal candidate for application ranging from clean energy to advanced catalysis and environment remediation. As research continues to evolve, carbon nanomaterials are expected to play a central role in shaping a cleaner, more sustainable future. Despite existing challenges in cost and scalability, the ongoing advancement in synthesis and functionalization are rapid, pushing the boundary for their practical applications. And finally, carbon nanomaterials are not just material for the future, they are the foundation of the next generation of eco-conscious technology. Thank you.